We're live.
Yes.
Okay, well, today we're launching some software on opensensors.io, and that's what we're going to talk about. It's all to open up a service to allow everybody to publish data from their sensors. So,
yeah. And this is in recognition of the fact that, like the last speaker, the kind of when we're building and we're kind of getting rid of the barriers between the digital world and the physical world, we have to be very, we have to think about citizens and the people and the communal spaces. So we're kind of going into building software that is transparent. It's all open source. If you want to create your own private networks, go ahead and do so. But also, if you're creating services for communal spaces, then the data should be open and other people should be able to reuse it and build services. And what we're aiming to do is basically make it as easy as possible so that we all don't have to reinvent the wheel. I see quite a lot of that happening within the IoT space at the moment. Is everyone's saying, well, we're going to build our own clusters of software that don't necessarily talk to each other, and it's not really necessarily about protocols. It's just making things available in a communal way, and encourage the idea of citizen science, because people they don't want to necessarily become consumers all the time. They would like to interrogate data sets for different reasons. We're talking about pollution data. Like I'm interested in the health side of it for my children that have asthma. Others are interested in the environmental aspects, and we all shouldn't have to put our own devices. We should be able to share and communally use the data.
So we want to enable developers to build services for their communities. So why open sensors and why is open source important? We are very used to trading our privacy and security and our data with large private corporations in return for convenience. And I think we do that too readily, and we trade our privacy and security for all time when we do that. In order to be confident that we can own the data that we create and derive information out of that data that we can all use together, then we need to take back the privacy and security and own it ourselves. So how do we do that? Well, what we're trying to do in Open Sensors is provide convenience for people to use a service on the cloud, if you will, to send data in. But because we're making that open, if you choose perhaps in a later part of your project that you want to own that data yourself and own the infrastructure, then you can go to opensensors.io, fork the code base, and build your own system. And so by developing this open and transparently and making it a community project, it means that this system can be owned by the community, and that if you don't trust us with your data, and really why should you, you have the option to go and fork it and create your own system and use that data in your own ways, particularly for areas where you want to control the privacy and security of your own data. I'm a technologist, and I'm really passionate about building reliable systems. I was late to the conference today because I arrived to London, and I tried to get a bus here, and I went with my Oyster card, and I went to the bus queue, got into the bus queue, arrived at the bus, and I put my Oyster card on the terminal reader, and there was nothing, no beep. And everyone was sort of getting a bit anxious, and I had to leave the bus. And so I took it back, and I thought, well, now I need to find a way again to Shoreditch. And I could have got some money out of a NatWest terminal, a cash point, but apparently there was a computer glitch yesterday causing all the cash points to go down. It's funny, that word computer glitch, because it's the sort of word that you only see on the front page of a tabloid. It's a tabloid word that, oh yes, the whole network went down because of a glitch. It's not a glitch, it's a software crisis that we're living in. It's a software disaster. And in that software disaster, we've created languages that allow us to create vast systems. I've seen many, many systems that have upwards 1 million lines of code. And many, many of the systems that we build are not reliable, and they're very, very buggy. So not only do we have unreliable technology, but we have vast monolithic code bases. And in that perfect storm is we're preparing to set sail 1 trillion devices onto that infrastructure. Disaster waiting to happen, I don't know. But for me, reliability, it goes hand in hand with providing reactive software, because there's no reactive software unless you have reliability. Case in point, I actually got on my Boris bike today, having not succeeded on getting onto a bus, and I tried to get here. And when I arrived here, I didn't know where to put the bike, and you've got to put it somewhere. So I got my phone out and I got this Barclays app, and I waited for 20 minutes waiting for spaces to arrive on the screen. And in fact, I was able to, half an hour later, to take a picture on my phone, and there was no spaces at all. And I know what was going on. There will be a server somewhere with all the information on all the spaces, and there'll be some deadlock, some software problem. And that's the reason I couldn't even park my bike. And it was it was interesting, because I got here late and we didn't get to prepare much of this presentation as a result. But this was the reason. I thought there was a real reminder of how dangerous it is to build infrastructure on stuff that isn't stable. So strong foundations mean strong languages. And we've chosen a language, Clojure, because it's a functional language. Functional languages are for getting rid of all of the kind of glitches and bugs, memory leaks, race conditions, deadlocks, issues with software that we see day by day. We use functional languages because they have mathematical foundations and allow you to build code that is far more resilient and far less buggy than what we've been able to build thus far. So for us, it's a kind of no-brainer to use a functional programming language. We've chosen Clojure because it gives us a way of accessing rich number of languages and part of the ecosystem that's available to Java developers.
Because my background is, I used to build 1 million lines of code in Java systems for years, and when I left that ecosystem, I started working in Python, and Python is beautiful, and I still I love it in so many ways. But when you're talking about building systems or analyzing data on terabytes, unfortunately Python just kind of creaks at the seams, and you need the horsepower of the JVM to enable you to build these systems. But at the same time, there's 2 of us, and we're running infrastructure that possibly nearly equivalent to what I was running in bigger teams of 20. And whilst I'm not a Clojure expert as yet, my productivity in Clojure and what I can produce has been absolutely phenomenal. So it's quite a pragmatic choice, but as well. This is really our choice to scale craft, if you will, since there's only 2 of us at this stage. We don't want to write large systems with lots of lines of code, but we do want to write those systems that are going to be, we don't want to be debugging them for the next 10 years. So we're creating an end-to-end reactive system. What does that mean? It means to eliminate polling and thus make things scale. So we have a pipeline from the device. This is our current architecture. So we take device and we use MQTT that we heard about yesterday. That at the moment we're using RabbitMQ because it's just a simple broker, and we're using the MQTT adapter of RabbitMQ at the moment. As we scale up, we may revisit that decision. When RabbitMQ receives that message, it pushes the message via AMQP, another protocol, to a system called Storm, which we're going to talk about in a little detail later on. Storm
is a push system itself, it will try to get information out of that data. We heard that data is not the same as information. We have a vast sea of data coming in. How do we make sense of it? Storm and some other technologies are our approach to extracting information and useful information out of the data. But it's also important that we can do that at scale, but it's also important that we don't lose data and we don't have the system crash on us and fall over. So Storm is a system that's designed to allow bits of it to fall over, but for it to still be resilient. If it does lose messages and does lose jobs and work, that it guarantees that it will restart those jobs. So it tracks every single packet that goes through the network, and you can build vast Storm clusters. So it's there. The only thing you have to really know about Storm is its reliability. There's a lot of complexity in Storm, but it's to achieve that real fail-safe reliability. Once Storm has found some data and found a result, a data tuple to push, it will push it back to RabbitMQ, and then it will. We listen to RabbitMQ using a technology called Machine Head, which is a closure wrapper on Paho, which is a Java library for doing MQTT. We're just a subscriber to that, and then we use core async and communicating sequential processes, which is a library, a technology that the Closure got this year. I spoke about it a little bit yesterday. And we use that to bridge over to the browser. So this browser that we're running today is a thing, it's an internet of things. This presentation slide deck is also a thing, and we can listen to messages. So publishing is very simple. Subscribing to messages is equally simple. And as messages come through, we receive the message in the Closure backend, and then we use server-sent events to send the data to the browser. The reason why we've chosen this stack is that we feel that we want to give people the means to create reactive dashboards for their data, so that when there is an important event, that you can push it to people's information console when and where that happens. This is a diagram that really just explains what I've mentioned. The circle in this case is a communicating sequential process channel. The rectangles are processes, and the use of channels means that if there is a data glut in the system, the difficulty of building these asynchronous systems is how do you dampen down the load? When they launched the Millennium Bridge over the River Thames a few years ago, when they let everybody walk across the bridge, they found that the bridge started swinging unsafely from side to side, and it was because the bridge wasn't designed to take that load. By putting dampeners underneath the bridge, they repaired that. They were able to take the load, and they were able to dampen it down. And by having channels which allow you to create your buffers, you can achieve a very similar effect, not just between systems, but inside your systems, which is a really valuable tool. It's very handy to have one single way of doing things, one single approach for doing asynchronous work. We have dozens and dozens of buzzwords that we all have to learn as technologists. So it's handy to have things, languages and paradigms that work on the server side as well as in the browser. So we've been careful to pick technologies that which work in much the same way between the back end and the front end. So the technologies that you see driving this slideshow are very much the same as the technologies you see driving RabbitMQ, Storm, and the core async services that we're building on the back end.
And also I think we've kind of made a design choice to make very small composable systems rather than, if you look at our code base, it's on GitHub. You'll see very kind of small, succinct files rather than kind of lines and lines of code, because we're very aware that this is very new and early. We just want to be able to kind of throw parts away and put them together again without affecting or compromising the whole system.
Yeah, And in that way, we've avoided things like single global event loops. We've tried to create everything very, very component-based so that we can compose solutions for individual data projects, either hosted on our own services or actually hosted on yours.
So, if I kind of roll back a bit, the reason that we started this project is because a research centre approached me about dealing with their IoT data sets. They had apartments, 20 odd apartments, and each had about 40 sensors. And they were dumping all of these data sets into MySQL database, and they weren't doing anything interesting with it. This whole project came out of actually the fact that they wanted to be a bit more intelligent about their alerting systems. In terms of, they were concerned about enabling people to live, elderly people to live in their homes as long as possible. So they had people with probably dementia and other illnesses. So they wanted to build alerting, and I used their historical data sets to pretty much have real-time machine learning models. And these models aren't a sense that everyone has to wake up, for example, at 8 o'clock. It is to actually understand an individual's either kind of patterns and movements and how they interact with their own space. And if it, what's called anomaly detection, if they kind of completely go away from their, within the boundaries of what they normally do, tell a neighbor or something, kind of a small amount of alerting. We also made some machine learning models on kind of whether somebody's fallen over, and then having the alerting be appropriate rather than complete using a brute force approach. And there is a lot of these kind of thoughts that we're having in the background is how do we how to make spaces responsive but also not very I guess kind of preserve the privacy and individuals to live in the way they want. And I don't know if we still have figured it out, but it's a process, and it would be nice if there was more open hardware that we could do these things with. Things like Fitbit would be great if they had more sensors, but allowed people to take the data and do what we like with it. A lot of the sensing we do at the moment is using phones and so on, but you know, it's just, I think that we have the software, and I think we have the data side. The hardware, like to re-emphasize, that's what's lacking. And hardware manufacturers need to be aware of the fact that it shouldn't just be, I'm going to give you this and you're going to consume it. People should be able to pick and choose the services that they can have within their homes. And having kind of multiple vendors, as it were, to be able to build services. It's an interesting challenge, and I think unless we solve that, I think IoT is probably going to, in my opinion, just kind of not be as innovative in the next couple of years.
So, a few notes about Storm for you, that it's the reason that we're talking about Storm. Jono said yesterday that a few years ago, yes, we had the devices. We've got yes, devices are important. The fact that they can talk to the internet is important. IPv6 is important, and events are important. But if you've got all this huge amount of data, what then? There is another revolution going on, the big data revolution, is how do we harness technologies today to make sense of vast amounts of data, and that's the real, I suppose, the coming together of those two trends that makes this very exciting. So Storm is a very capable technology, but it's very sophisticated, it's very difficult to set up, and it's very expensive to maintain and run. If you're an IBM or a Microsoft, you can build your infrastructure privately. If you're actually interested in putting a radiation sensor or something on a bicycle, are you going to build a Storm cluster in order to process that data? And we feel that if you set that expectation, then you're setting the barrier very high for people to make sense of this data. So by providing this as a service, and providing people with the tools, and by showing transparently how those tools are put together by being open and being open source, then we're hoping that it will lower the barrier for entry so that people can access big data technologies, but without having to spend years in the big data domain. So that's what we're trying to achieve.
Because I mean, in terms of, if you look at one sensors or even a cluster of sensors, in a way, the information isn't very interesting. It's the value, it's the pollution value or anything else. But it's when you put it on a map, when you put it in context with other data sets, and you start kind of knitting all of the open data set information out there, that it actually becomes very, very valuable. And the value is for all of us. I mean, it's not just for advertising. There's so many kind of problems we can solve, and interesting problems that possibly as technologists, I don't know, maybe we think we can solve them all. But I'm actually an optimist in a sense that if we give people the tools, something very exciting things will happen.
Definitely. So that's us, Open Sensors IO. We're launching the software today. Do feel free to download it and give us all your feedback, and that would be great. Thank you very much for